Okay, let's unpack this. Forget everything you think you know about computers working with simple on or off switches. Imagine computing that exists in a state where things can be both on and off simultaneously, sort of a reality-bending machine.
And the truly fascinating part is, well, that mind-bending concept isn't science fiction anymore. We're diving deep today into the world of quantum computing, and we're really zeroing in on what looks like a significant breakthrough, Google's Willow chip.
Exactly. Yeah, we've been wading through some, well, dense, but ultimately fascinating sources covering this technology. Our mission here really is to pull out the most important nuggets, understand precisely what makes Willow a potential game changer, and maybe most importantly, what this all could mean for the future, especially when you think about AI.
Right. And to get us oriented, let's maybe start with the absolute basics, just to highlight the difference. The
Yeah.
computer you're using right now, your phone, your laptop, they all run on classical bits. Think of it like a simple light switch. It's either on or off,
Hmm.
0 or a 1. Simple.
Right? Definite, clear states, nothing fuzzy about it. But quantum computers, they operate using qubits, and this is where you leave that simple light switch reality behind. A qubit can exist in like a combination of both 0 and 1 states at the same time.
hmm This simultaneous existence is thanks to a quantum property called superposition. The go-to analogy, and it's a pretty good one, is a spinning coin. While it's spinning, you can't really say it's definitely heads or definitely tails, can you? It's in a state that's a mix of both until it finally settles, until you measure it. Qubits are kind of like that spinning coin.
Okay, so you've got qubits that can be in multiple states at once. Superposition.
Mm.
But here's where it gets even weirder and honestly really interesting. Qubits can also become entangled. This is the phenomenon Albert Einstein famously, maybe a bit skeptically, called spooky action at a distance.
And it is genuinely spooky. Imagine you have two magical gloves, created together. You box them up, send one to the other side of the universe. The instant you look in your box and see, say, the right-hand glove, you instantaneously know the other box contains the left-hand one. Doesn't matter how far apart they are, their fates are, well, linked.
So it's these two core properties, superposition, this being in multiple states, idea, and entanglement, this bizarre instantaneous connection that unlock the immense potential power of quantum computers. They aren't just faster, necessarily. They can explore this huge landscape of potential solutions all at once. In a way, classical computers just, well, they just can't.
Which naturally leads to the question, if they're theoretically so powerful, why aren't they everywhere already? Replacing all our data centers. And the major hurdle has always been that qubits are incredibly fragile, extremely sensitive. They're like the most temperamental performers you can imagine. The slightest bit of noise from the environment, heat, vibrations, stray magnetic fields, it just knocks them out of their delicate quantum state, causes errors. So keeping them stable, keeping them coherent long enough to actually do a calculation, that's been the monumental challenge.
And that is precisely where Google's Willow system enters the picture as such a significant potential breakthrough.
Yeah.
It directly confronts this error problem head on. What Willow appears to have achieved is something, well, it sounds counterintuitive based on the sources. It makes errors actually shrink as you add more qubits to the system.
Right. Usually adding more parts, more complexity, just introduces more places for things to go wrong, more failure points. But with Willow, the sources describe it almost like building a puzzle that gets easier the more pieces you connect. Or maybe like constructing a skyscraper that becomes inherently more stable with each additional floor you build. It kind of flips the script on the whole scaling
Yeah.
problem.
And the sheer performance difference they demonstrated, it
Mhm.
was just staggering,
Yeah.
really. The sources highlight one specific task Willow completed in under 5 minutes.
Okay.
Under 5 minutes. The estimate for the fastest classical supercomputer to do the same task. 10 septillion years. I mean, that's literally a time frame longer than the estimated age of the universe. That number alone just, wow, it drives home the difference in potential.
Yeah, that kind of performance jump, it takes us back to a theoretical concept Peter Shor proposed way back in 1995, the idea that you could actually correct quantum errors. For nearly 3 decades now, the big goal in the field has been to reach what's called the fault tolerance threshold. This is the critical point where, counterintuitively again, adding more physical qubits actually starts to reduce the overall error rate of your computation, not increase it. Willow seems to represent a major step, maybe the major step so far, across that long-sought threshold.
Okay, so how exactly does Willow pull off this trick? This making the system more reliable by making it bigger.
The sources we looked at detail basically three key aspects of their approach. First, they're using what's described as state-of-the-art error correction codes. They showed that as they scaled up from smaller groups of qubits to larger gridded structures, the error rate went down exponentially. Second, and this is absolutely vital for actually completing a useful computation, Willow implements real-time error correction. It's not just detecting errors after the fact. It's more like trying to balance that spinning top we talked about earlier. You have to make constant, instantaneous adjustments whenever it starts to wobble. This continuous monitoring and correction, it's essential for maintaining that fragile quantum state all the way through a calculation.
Right, active management. And the third point is what they call beyond break-even performance. This one's interesting. We use redundancy in classical computing all the time. Think backup servers, RAID arrays in your computer to improve reliability, make things more robust. Quantum computing does something kind of similar, but the sources explain Willow is actually surpassing a crucial threshold here. They combine multiple physical qubits.
To create one single logical qubit.
Yeah.
And the critical insight, the real important part here is that this logical qubit, which is made up of several physical ones working together with the error correction, this logical qubit has a lower error rate than any single physical qubit could achieve on its own. Crossing that break-even point means the error correction isn't just, patching things up. It's actively creating a more reliable, more stable unit for computation than the shaky underlying parts. This is a fundamental step towards genuinely reliable, fault-tolerant quantum computing actually becoming practical.
Okay, so we've dug into how Willow is tackling this fundamental problem of errors, taking a big step towards fault tolerance. Super
Yeah.
important. But what does this breakthrough really enable? What are the downstream effects? Let's pivot now and talk about the exciting potential applications, particularly where quantum computing meets artificial intelligence. That seems like a huge area.
Absolutely. If we zoom out and connect this to the bigger picture, one of the most immediate and maybe easiest to grasp impacts could be on AI training. Training today's really complex AI models, like the large language models everyone's talking about, it requires just immense computational power. It can tie up the world's biggest supercomputers for weeks, even months.
Yeah, it's a massive bottleneck.
Yeah.
Quantum computers, though, with their ability to process vast amounts of data and explore problem spaces in parallel,
Mm.
they could potentially just collapse those training times
Yeah.
dramatically. The sources suggest this could go from months down to potentially minutes. Just imagine how rapidly AI could evolve then.
Yeah.
You could develop and test much more sophisticated models, tackling increasingly difficult problems much faster.
And it's not just speed. This capability also throws open the door to ultimately, the combined power of quantum processing speed and AI's knack for finding patterns and relationships within complex data could make currently intractable problems, well, solvable.
And the list of potential challenges from the sources is long and pretty impactful. Things like optimizing incredibly complex global supply chains in real time, discovering and designing entirely new materials and drugs at unprecedented speed, like we mentioned, getting much better, more reliable predictions for climate change effects years or even decades out,
Mm.
and optimizing the logistical flow for entire cities, traffic, energy, resources to improve efficiency and reduce congestion. These are massive real-world challenges.
Huge challenges, the kind where classical computers just hit a wall because the number of possibilities explodes.
Exactly. They hit fundamental limits.
Now, while breakthroughs like Willow are incredibly exciting, it's important, to keep our feet on the ground a bit. We need to acknowledge the challenges that still remain. Current quantum systems are still astonishingly sensitive. They need these highly controlled environments, often cooled to near absolute zero temperatures. That's not easy. And building these large-scale, fault-tolerant machines is still an immense engineering difficulty. We're not there yet across the board.
Absolutely. We're definitely still in the early chapters of this story. It's not like you can buy one at the store next week.
Yeah.
But the overwhelmingly positive takeaway from the sources, I think, is that developments like Willow demonstrate that these challenges, while definitely daunting, are not insurmountable. The significant investments being made by companies like Google, IBM, and many others, they're clearly starting to yield tangible, measurable progress.
Yeah, the quantum future isn't some abstract concept safely decades away anymore. It feels like it's becoming a tangible reality. We're seeing the potential transformations lining up on the horizon across multiple industries. Cryptography is a big one, obviously, but also drug discovery, materials, science, finance, climate research, so much more.
So let's wrap this deep dive up. We are, it seems, standing at the very edge of a new computing era. We're pushing past the classical limits that have defined computation since its inception. Willow isn't just a technical achievement in a lab. It feels like a concrete demonstration that we are making significant, measurable progress towards building practical, large-scale quantum computers.
And it's not just about raw speed, although that 10 septillion year figure is hard to ignore, isn't it? It's really about creating fundamentally new tools. Tools capable of tackling some of humanity's most complex, most persistent, and most impactful challenges.
So, the quantum revolution, it's poised to fundamentally alter our understanding of what computing can even be and what problems are actually within our reach. As you think about the incredible power of the devices you hold in your hand right now, your phone, your computer, consider this. What stands out to you about the sheer scale and complexity of the problems classical computers cannot solve today?
And now, truly ponder this. How could a technology capable of completing tasks in minutes, tasks that would literally take longer than the age of the universe for our current best machines, how could that reshape our approach to knowledge itself? How could it accelerate discovery and potentially allow us to tackle those biggest, thorniest issues facing humanity in completely new ways?
The future isn't some distant horizon. It feels like it's happening right now, one qubit at a time.